The physical quantities like position, linear momentum, kinetic energy have certain operators associated with them. Operators are mathematical action on functions which produces a new function. For example, when operator A operates on f as a function of x, then we get a new function at g as a function of x. So, squaring can be an operator as well as differentiating can also be an operator. While discussing about operators, we should keep in mind that they are supposed to act on those functions only which are possible wave function of a particle, that is, which are finite, which are continuous, and which are square integrable. Now, square integrable means when we integrate the probability density of the wave function from minus infinity to plus infinity, then we should get a positive finite number. Now we will talk about linear operators. Let us suppose that we have an operator A. An operator A is called linear operator if it follows the following condition, that is given by here f as a function of x and g as a function of x are two arbitrary functions and c is arbitrary constant. As per the first condition, we can see that when operator A operates on the sum of two functions, that is f as a function of x plus g as a function of x, then this result must be equal to when operator A operates on individual functions f as a function of x and g as a function of x. Now, as per the second condition, we can see that when operator A operates on c multiplied by f as a function of x, then c being a constant comes out and we have c multiplied by operator A operating on f as a function of x. Now, operator algebra. If there are two operators A and B and an arbitrary constant c, then we define three new operators a plus b, ab, and ca as the following. So from the first condition, we can see that when you have the sum of two operators a plus b operating on the function f as a function of x, then those two functions get distributed over the same function f as a function of x. So here we have the product of two operators, that is ab operating on the function f as a function of x. Then here first operator b will operate on the function f as a function of x. Then the result which will obtain when the operator b operates on the function f as a function of x, then in that result operator a will operate. Now in the third condition, we have ca operating on the function f as a function of x, where c is a constant. So since c is a constant, c will remain outside and we have operator a operating on the function f as a function of x. So now we have a question to check whether the following operators are linear or not, and in the first operator a we have multiplication by x and the next operator b is given as squaring. So now for the solution, let f as a function of x and g as a function of x be two functions of x. Let a denote the operator multiplication by x. So now we'll apply the first condition of the linear operator, and here operator a will be operating on the sum of two functions f as a function of x and g as a function of x. And since operator a is multiplication by x, so we'll replace a by x, and this will be equal to x operating on the individual sum of two functions f as a function of x and g as a function of x. So here the first condition of linear operator is satisfied. So now for the second condition of linear operator, we have operator a operating on c multiplied by f as a function of x, and in place of operator a we'll add x, and we have x operating on c multiplied by f as a function of x, and this will be equal to c multiplied by x multiplied by f as a function of x, and this will be equal to c multiplied by operator a operating on f as a function of x. So here both the condition of linear operator are satisfied, and hence we can say that the operator a is a linear operator. So now we have the another operator as squaring, and let a denote that squaring operator. So now we have the operator a operating on the sum of two functions, that is f as a function of x and g as a function of x, and this results in f as a function of x plus g as a function of x whole square. So here we can see that operator a operating on f as a function of x results in f as a function of x whole square, and operator a operating on g as a function of x results in g as a function of x whole square, because operator a is squaring. So here we can see that the first condition of linear operator is not satisfied, and hence we say that the operator squaring is not a linear operator. So for the next question, we have operator a as multiplication by x and operator b as differentiation with respect to x. So we need to find a plus b sin x, b plus a sin x, ab sin x, and ba sin x. So for the solution, we have a plus b whole sin x equals to a sin x plus b sin x. So here we have used the property of operator algebra, and since the value of operator a and operator b is x and dy dx respectively, so we get our final answer as x sin x plus cos x. And now for b plus a sin x, we have done the similar thing, and we get our final answer as cos x plus x sin x. So now for the third solution, we'll use the second property of operator algebra, and in ab sin x, first b will operate on sin x and we'll get cos x, and here in cos x, operator a will operate and we'll get our final answer as x cos x. And similar case is done with ba sin x, and we get our final answer as x cos x plus sin x. Now we'll talk about the commutator operator. So in the previous example, we saw that the value of ab sin x is not equal to the value of ba sin x, or simply we can say that AB is not equal to BA. But if we have operator A as d by dx and operator B as d2 upon dx square, then we will have AB is equal to BA. If we have two operators A and B, then we can construct a new operator C such that C is equal to AB minus BA. And this operator C is called the commutator of A with B. So now we have our question as simplify the computation of x with px, where x and px are position and x component of linear momentum of the particle respectively. So now for the solution we have position operator is equal to x and x component of linear momentum operator is equal to minus I h cut d by dx. And let fx be any function of x. Then we have commutation of x with px into fx is equal to x px minus pxx into fx, and this will be equal to x px into fx minus pxx into fx, applying the property of operator algebra. So now keeping the value of capital X as small x and px as minus I h cut d by dx, we get minus I h cut x dfx by dx plus I h cut d by dx of x into fx. So since we have d by dx of x into fx, we'll apply a chain rule, and on simplifying it, we get our final answer as I h cut into fx. So now we got the value of computation of x with px as I h cut. So now we'll discuss two important computation relations. So the first computation relation is computation of A with BC is equal to B multiplied with computation of A with C plus computation of A with B multiplied by C. And now the second computation relation is computation of AB with C is equal to A multiplied with computation of B with C plus computation of A with C multiplied with B.